So I did a master's thesis before my PhD in cognitive modeling. And so I'm going to talk to you a little bit about it today. And I'm going to tell you all about why I think it's cool. So before we begin, let's just get a handle on some of these terms. I just want to ask everybody, what comes to mind when I say the word architecture? Just any free form, kind of put it in the chat or yell it out. Architecture, what comes to mind? Professor Merkley will moderate the chat.
Well, I said houses, and then other people are saying structures, buildings, blueprints.
Yeah, good, exactly. So blueprints. Blueprints of a house, for example, shows the different rooms, shows the internal structure. And that's kind of what we're trying to do with cognitive modeling and cognitive architectures is to create a blueprint, a working blueprint of how the mind and the information processing works. So if you remember this video from Freud that I posted a little earlier, where he talks about the metaphor of the mind being a house and his consciousness being a lonely light and all the other rooms are dark. Very, very neat metaphor. But this is one of the things that the science of the mind is trying to achieve, is trying to understand how the different rooms in the mind interact and how we can understand their functional nature. And so cognitive modeling, why? Well, to create a working blueprint of cognition. How? We'll talk a bit about this. It's to integrate neurological evidence and then test it. Each model is its own sort of hypothesis. And what is it? Well, we're going to talk about that right now. So cognitive science, there's many different perspectives in psychology. Freud had sort of his psychodynamic model. Then we talked about behaviorism, how it had sort of just trying to understand what's going on in the mind by stimulus and response. And so our home in cognitive science is an information processing perspectives. And these are all very valid perspectives, but this is our home. So why computation? Well, again, it gives us information processing explanations. Computation is uniquely situated to grasp slippery concepts, can force clarity because computation does not work well with, if you ever talk to Siri, you know, it doesn't work well with ambiguity, and it's testable. But the point is that, just as the quote on the bottom of the screen says, computer science is not about computers, just the way astronomy is not about telescopes. We're trying to see something. We're trying to use it as a lens for seeing something deeper than we can visually peer into. So again, a computational lens gives us information processing explanations. We see the computational level. If you remember Mars levels, you have the neural hardware, you have the software working above that, sort of that arises out of it as an emergent level. And we can get functional theories of how the different information processes in the human mind interact. So an architecture is the broad general idea. So here's a model of a motor. And the architecture would give you the general operations, a single set of mechanisms for all the processes. Now, we don't have that yet. We're still in the early days of building an architecture of cognition. We're actually building models right now in terms of trying to depict single phenomenon, trying to piece them together to see how maybe a single set of mechanisms would describe all that. So for example, in a psychology lab, you might have a very simple process where you get a subject to press a button. If you see a turtle, press the button. If you see a rabbit, don't press the button. Very simple, but we try to understand sort of how that simple process might work in cognition. Then you can have a model of how somebody might kick a soccer ball. Then you have a separate model of how somebody might drive a car, start the engine, release the clutch, and I'm dating myself there. But you had to have these different models of how cognition directs behavior. And then maybe you can try to figure out what must the architecture be like for a single set of mechanisms to give rise to all those different instances, pressing the button, kicking the soccer ball, and driving your car. And this is how we are trying to unify our understanding. And so cognitive modeling is a process model. It functions over time. You can't really see it in a two-dimensional picture. but it tries to depict how psychological processes function over time. And it represents cognitive processes as computer code. Now, it's a bit of scary. We won't really get into code because it still freaks me out a bit. But this code instantiates neurological data. It can be tested empirically. It produces runnable simulations using algorithms. And it can then represent deep components of the mind in a way that's systematic, it's well-defined, and there's no hiding. If it's wrong, at least we can say this is clearly wrong, it doesn't match up to data, and we can be honest about that. So this is how it connects to the larger history of science by building theories of empirical phenomena that are tested and adapted based on data. Yeah, so it has to do with computational theory of mind. Now, we talked about this in one of the videos about how the theory, one of the theories that cognitive science is based on is that the nature of mind is computational, or if you don't want to think of it literally, you can think of it as a metaphor. There's input, say vision comes in, the information is transformed by your processes to bring up knowledge of what those things are. Then there's output in your behavior. Let's say you driving your car, visual information is coming in, the information is being transformed to direct your behavior as an output. So you can drive straight down the street, go to the store, do anything that you normally do in your normal life. So again, you can take it literally or as a metaphor. Now, David Marr, who thought of the levels, thought of it as a useful metaphor. He didn't think they were real, but he thought that there was some useful way of, it was a useful way of thinking about it. Alan Newell was a different guy who created the first cognitive architecture, thought it was real. And then he went to the mat for that. And he said, no, these levels are real. Neurons are real, computations are real, and the knowledge that we direct with our algorithms are real. Everything's real. It's just different ways of thinking about it. So here's a little video.
Can I ask then, is that
Yeah.
the key difference in your mind between Marr's levels and Newell's levels?
Yeah, okay, good, great. So there's a slight difference in that Marr, when he originally came up with these levels, was talking about vision. And he was thinking about how just visual input. So he was more thinking of a model. And so he thought of neurons as hardware and algorithms, and then he put computation at the top, which had to do sort of more with the functional process by which you're trying to, you know, look at something in the world in order to do something else. But Newell said, now, if these are real, let's think about it on a slightly different. Yes, there's the hardware. There's the neural hardware that gives rise to information processing, but on the middle level is the computational level. That's the second level. And on the top level is the information, the knowledge that the computations move and interact. So hardware, computation, and knowledge level. So that's kind of how I'll be talking about it. And since he was the guy who created the godfather who created the first cognitive architecture, that's kind of how I use the computational level to think. Hope that answers. Did that answer it clearly?
Yes, thank you.
Okay, great. Okay, so here's some other.
Actually, I'm going to rephrase it just so it's clear in my mind. And
yeah, please go ahead.
Well, just so in my, I don't know Newell's levels as well, but in my view, his problem with Marr is that like the computation and algorithm levels in Marr kind of conflate two things. Is that inaccurate?
Yeah, they're a little fuzzy. So
yeah.
He would talk about the algorithmic level, but he'd also kind of put representations, knowledge kind of a little bit in there. And then he'd talk about the top level, and he'd also as the computational level, which is if you separate algorithms from computation, it makes a little fuzzy in my head since they're kind of the same thing. But this idea of levels was groundbreaking. So Newell took it, made it a little clearer for some people, for me, to think about, where he put computation on its own level, the algorithms, the processes that happen underneath the surface. And then he put knowledge on top, which is how we see the world. So you're looking through, at the world through an interface of symbols. I mean, how you see the world is not how it is. It looks like we're looking out into the world, like looking out through a windshield in our car, but we're not. We're looking at symbols in our head. And then underneath the surface of our mind are algorithms and processes, computational level that's moving things around and doing a lot of the work for us that we're not aware of. And that's what our neurons do. So neurons, computation, and knowledge level. Was that clear?
Yes, thank you.
Okay, yeah, okay, good. Okay, so computational modeling isn't new. I mean, we do this with a lot of things and they're very useful. So for example, weather, the world was changed by understanding weather a little better with computational modeling of weather. We can get an understanding of the features and the attributes of weather, how wind works, and we can have predictive models that are very accurate. We can also model car engines. Engines, there's input, there's this transformation, and then there's output. Say the wheels move as a result, and this is how computation can model weather, can model the brain, can model. And so there's the computational level we're trying to model that gives rise out of the brain. So there's these processes that happen inside the different rooms of the house, and we're trying to understand how these work. And this is what we're going to be using, talking about today, is the common model of cognition, which depicts the different rooms in the house of the mind. There's perception, you see there's declarative memory below, there's motor output. I know it's a little weird right now, but we'll talk about it a little more. Okay. So back to black and white, sorry, but this is kind of how it all started. Back when there was black and white pictures and we were just still muddling around with what is the mind? What's going on here? There's clearly the most important and most interesting thing in the universe, as far as some people are concerned, is the space between our ears. And so we're trying to empirically study the mind, use the scientific method to accumulate data. And we accumulated a lot of great data, and a lot of it helped our understanding. For example, for most of our life on Earth, humans didn't understand that their brain was made out of neurons, or that we even thought using the brain. Aristotle thought the brain was just a radiator for getting rid of heat, and that thinking came from inside your heart. So just knowing that thinking and processing happens in the brain was a big leap. And then as we studied the brain, all this data came out from our understanding. But one problem was that a lot of the information was becoming fractured. It was just kind of flying all around, sort of like a snow globe. Everyone has the idea of shaking up a snow globe. Imagine all those facts about the brain flying around, not integrating, just kind of obscuring our view of what cognition is. At least this was one fear, is that so many fractured ideas that weren't integrating, if we just, thought down the road a bit in history, it's just going to create more and more fractured, ununified information. And we're not really going to get anywhere if we just have a lot of neat ideas that don't tie together. And so there was a call for unification. This is Alan Newell. And he called in his Harvard talk in 1979, I believe, he talked about how we need to start integrating this data into models. How do we create parsimonious information processing explanations that can account for the different empirical phenomena that we're witnessing of how the human brain works, whether it's just driving a car, whether it's writing strange things on a blackboard, whether it's giving a lecture. We need to have some understanding of how all the information we're getting out of empirical data is being integrated. So neuroscience was pivotal in terms of mapping the neural connections in brain regions. We call these connectomes, sort of a wiring diagram of how all the different regions in the brain connected and process information between each other. And there's no single region that does one thing. Now, there we talk about networks of regions, but we can abstract out of these networks into nicer little diagrams on the right. You can see how the different areas that were empirically derived on the left, such as long-term memory, motor, working memory, then became diagrams to see how the functional connections interact. You see long-term memory, procedural memory, perception. And so here's another question. Who remembers the difference between, this is kind of going back to your psychology information, but who remembers the difference between declarative memory and procedural memory? These are two parts of memory that were empirically recognized to exist in the brain. So if you want to just put that into the chat, you can just kind of remember the difference between declarative memory and procedural memory. You can just kind of
Kyle
yell.
says procedural is skill-based.
Yeah.
Can you give an
Good.
example of a skill, anyone?
Example of skill.
Like biking. Yeah.
Yeah.
So we do that.
I'm glad you said that. Want to know why? Because that was my next slide. So full points. Not that you're getting points, but so a bike, knowing what a bike is, the fact is declarative. Knowing how to ride a bike is procedural. I mean, you can know all the information in the world of what a bike is, facts about the bike, but you're going to hurt yourself if you get on a bike just knowing the facts. You need procedural knowledge of how to run that bike. So these are empirical derived facts about the brain, that there are these different parts of cognition that enable us to create little diagrams that instantiate it. So for example, you have declarative memory in the left and procedural memory in the right. And in cognitive modeling, we would then say, well, what kind of units? What's inside of it? And so, for example, declarative memory on the left, you might have units of facts. Bike equals, it's a transportation vehicle. It's made out of metal. It's got spokes. It's got, you can get somewhere on it. But procedural memory has its own units of how to actually do it. If you're on a bike, then pedal. Otherwise, you're going to fall over and hurt yourself. If you're on a bike, steer. So it actually moves the whole system. And I have a little video about how these units of can be computationally instantiated to see how they work together a little better. So for example, you have this unit of procedural memory, which is kind of like a conveyor belt. It moves information, it matches. If there is a condition, then it fires an action. If bike, then pedal, and knowledge can come up and say, that's a bike, it's for transportation. It can then direct procedural knowledge to then move your legs and in a practice way, showing how these different units in the mind can be computationally instantiated. And then you can kind of see how they work together to create behavior. That's a very toy model version. We'll show a little bit more about that later. But yeah, this is just a very neat example of how we empirically derive the fact that there are declarative memory, there's procedural memory. We cannot understand their nature. We computationally instantiate them. Facts, practical knowledge, procedural knowledge, and then we can kind of make models of how they run together. So these are units of cognition. Someone called them the atomic components of thought. And so by instantiating empirical data into computational units, we can begin to see how these units of information interact. We can begin to see their causal relations. There's procedural knowledge, there's declarative knowledge, there's the modules that hold them, and then there are these things called buffers, which are little containers that hold all, in working memory. And then we can build them up like bricks in a house. So we can see brick by brick, unit by unit, how they build up to build architectures, to build the different rooms in the house. And then we can test them. So again, the connectomes that were empirically derived, we take the information out, we get a better understanding of how they move and how they, okay, here's a little video of how we sort of derive the empirical information into, instantiate them into models that then we abstract out of and can understand how they functionally connect and interact. Back when they were starting to do this, there were all these different models. People were taking the empirical data and building different architectures out of them. They were all working independently, but they realized that all these different architectures had very common features, declarative memory and so on. And so they overlaid these into what's now called the common model. And so all the different architectures that were built up over the years, they realized they all had common features again. And so instead of fracturing the information, we started to unify them and started to unify all the common features into a common model of cognition. We all knew they all had declarative memory. They all had some form of procedural memory, all had some form of perception, some sort of motor output. And they all worked through buffers and so on. And so again, we're trying to unify them And this is the best we got so far is the common model of cognition. And this is where they get a little scary. There's all these different models, Clarion, there's EPIC, this is a very scary one. The EPIC cognitive architecture, you see very weirdly declarative knowledge, procedure memory, input-output functions. You have SOAR cognitive architectures. If you're confused, so am I, because this is all different architectures based on empirical data. This is one that I use, ACTAR, and it's a version of a common model. Input-output functions, declarative memory. So for example, a declarative memory in the right top hemisphere, they're all connected to brain regions. For example, you have a declarative module that's that connects to the temporal lobe and the hippocampus. You have visual model in the left, bottom left, occipital, manual module in the motor and cerebellum, and then you have the basal ganglia in the middle that has the procedural rules that run the whole system. And so again,
sorry, Brendan, I think you're going to come to this, but Sophie asked whether all of those are considered common models.
Yeah, they're considered, good question, they're all considered instantiations of the common model. So because they're all created separately, they're very confusing. And so there was so they're all considered versions of the common model, but they're created first. And so we took the common features of them. They all have their unique features. They all have their idiosyncrasies, but the common features were then abstracted out to create the common model. So it wasn't that the common model existed first and these are branches off. These started first and then with their own unique features, and we took the common features of all of them to create the common model, just to make it simpler. Look at it in the right there. Isn't that simpler? Isn't that nicer? Isn't it prettier? Doesn't it make you less scared to do cognitive modeling? I know it made me a little less intimidated. So just to summarize, we have the connectomes empirically derived. We abstract out of them, and we can create cognitive architectures that try to depict the different behaviors and the different cognitive processes that give rise to behaviors. Okay, so let's talk about Newell's cognitive levels a bit. So, of course, we have the hardware level. We have the hardware. The neural level forms the hardware, processes information. Neurons do this kind of fancy magic. It gives rise to computation. It processes information. It gives rise to the computational level that moves knowledge around. It gives rise to how we see and understand and direct our behavior throughout the world. And this middle level is the computational level. This middle level that I really want to drill home as drill into as the feature we're trying to model. This invisible computational level that gives rise to human behavior and everything we see humans doing in the world. It's very interesting, very, very difficult, but it's very, we got two of them there. Okay, so again, neural level, computational level. The invisible level is what our brain does when we're not looking. And understanding that will help us understand, finally, just what the brain's doing when it's doing anything. Okay, so now we're going to show how the computational or cognitive model works. Again, this is a sort of a toy model version, just to kind of visualize how these different processes work. So you have perception on the left, you have motor output on the right, and you have declarative memory below, and you have procedural memory, the thing that rides the bike, that moves the whole system in the middle there. Okay, so let's dive into the common model. So you have procedural, you have visual input, you have motor output, input and output, very computational. You have declarative memory in the bottom there. And then you have in the center procedural memory, which holds those procedural rules I was telling you about, little conveyor belts that send out instructions. They move information throughout the system. Through the buffers. The buffers are little containers that hold and move information. It's like working memory. So for example, say you have visual input and the procedural rules send out instructions to bring in the visual input. It connects to declarative memory and says, what is that blob? And the fact comes up from declarative memory saying it's a bike. And then motor output can then be directed to ride the bike. And these procedural rules in the basal ganglia, these are the little conveyor belts. They form the base of the architecture. These are the production rules, the procedural memory. So if there's a condition, then it fires an action. If bike, then pedal. And this is how they work through changing the states in working memory. These are the buffers. Buffers hold information. They're working memory. They're little containers that hold information. And the procedural memory are these production rules. See, all the buffers can be thought of as a single transparent box, and procedural rules change the state in buffers. And new productions rise up to match, and once they match, they then fire through the buffer again, working memory. New productions come up, rise, match, fire, change the state. And this is how information is moved through the system computationally. And it changes the states in buffers. Say, for example, you have a glare in your visual input, states change to raise your hand to maybe block out the glare of the sun. So there's input on the left, visual information, productions, procedural rules, procedural memory, changes the states in buffers and working memory to then direct your motor behavior to intelligently. I'm going to block the sun out. I'm going to drive my car based on the knowledge I have or based on the conditions that I'm, anything at all. So for example, knowledge can move into buffers as well, these little containers. Your knowledge states can move into your working memory from declarative memory. It moves up. And here's another little toy model version. And let me know if I'm going too fast. Was there any questions on that? Actually, that's maybe a good time to pause. Was there any questions on
there was a comment that there are buffers everywhere, but no questions.
True. Okay. So for example, so declarative memory is in the little green box at the bottom there. So all your knowledge lies in there. Everything that's you've ever known and can remember is in there, but it's not in your working memory. So it has to be brought up out of working memory into your mind. So if I ask you, anything, the knowledge is then brought up into your working memory. Who were the actors in Titanic? Who played Captain America in the Marvel movies? It was in your declarative memory. It then is brought up as a chunk into a buffer. So then you then have conscious access to Chris Evans, to anybody else in the Marvel movies, or any other bit of knowledge you've ever received. Even knowledge about declarative memory is in your declarative memory. Is then brought up into a buffer, and then you can then interact with it once it's in working memory. So every module, perception, declarative memory, motor, they're all static, and then they move their information into a buffer, a little container, and those containers talk to each other. The buffers talk to each other. And that's kind of your conscious working memory, if you want to think of them like that. So that's how buffers are the present now state of the system. So for example, some knowledge.
Oh, sorry.
Yeah.
Can I ask another question while we're talking about declarative memory? We had some talk in the chat because in the cognitive psychology / neuroscience model of memory, declarative memory is both semantic knowledge, like knowledge of facts, and episodic memory. So does a cognitive model have an episodic memory?
So in this case, you can have associative, it's structured as propositions. So yes, both of those are structured as propositional knowledge that we can say they're facts, but I didn't want to get too deep into the terminology, but we would instantiate both episodic and semantic knowledge as propositional knowledge that can then be encoded in declarative memory and brought up as the situation warrants into your buffers. But we would consider units of declarative memory to be propositionally structured. Is that clear, or should I talk a little more about that?
It's clear to me, but does anyone else want more explanation?
I understand it.
Okay. Anyone else? Ça va? C'est bon? Okay. And feel free to interrupt at any point. Again, I don't want to go too fast, but okay. So we talked about working memory, these little buffers, these little containers that hold the now state of the system, your working memory. So these knowledge chunks can come into your working memory, can come into the buffer to then direct the system. So you have knowledge of a bike come up into your working memory, and then that then directs you to get on the bike and start pedaling and have your working memory bring up procedural memory to how to ride the bike. So for example, say just an example of how knowledge instructions can come up. Say you're thirsty and you visually input, you see, oh, I should pause there actually for a second. So say you're thirsty and you have declared a memory below, and into your visual buffer, you can see water. And you can't really do much with that visual information until you have a production rule of procedural knowledge, bring up memory. And you know to pour the water into a cup. This is just, I mean, you could drink from the faucet if you wanted to, but this is an example of how you would have an instruction to pour the water into a cup, which then directs more production rules, procedural memory, to fire motor output to pour water into the cup. So this is object level cognition. Visual information comes in. This is the computational understanding of how visual information comes in. See the water, that brings up, a production rule to fire, to draw up knowledge into your working memory. An instruction says pour the water into a cup. This draws up more procedural rules that then activate motor output to then pour water into a cup. And so this is a very simple way of showing how we can computationally instantiate our understanding of the brain into these little units to see how the units functionally interact. So there's a lot more knowledge than just one chunk. There's a lot more productions, more procedural knowledge than just these little ovals, but this is just a little flow chart to see how they all work together. Okay, I'm going to pause there because I want to know if there's anybody who has any questions or whether this was confusing at all, because it very much can be, I know. Any questions?
There aren't any in the chat. Although now I'm thirsty.
Yeah.
I forgot to fill up my water before class.
We can pause for a water break, actually. Okay, all good for now. So let's move on to the scary part. So this is all instantiated in code in ACT-R, which is a version of the common model that I use, that I showed where all the different modules are connected to the regions of the brain. These regions are there in runnable code, which creates the actual process model. So you can see, isn't it beautiful, the code running? The code on the left depicts the different modules and how they interact. And then the code on the right is the actual running. And it takes a lot longer to write the code than to show you, I can promise you that. But this is just, I wanted to actually just give you a scary glimpse at how the code runs, but it's written in Python, and it's ACT-R is written in Python, so it's another programming language that depicts the different empirical data of how cognition works. Okay, so way back when, I think you remember the historical video of Turing in the 1950s, 40s. They were so excited about building artificial intelligence. They said, man, we're so close to building artificial intelligence. All we need to do is put this code into this hardware, move it around a bit, and eventually we'll get these intelligent agents that derive out of it. And yeah, they did build some very simple cognitive models in these little architectures. It wasn't the common model, but they could show how some perceptual information moves around, and declarative memory can move around. But they were very brittle. They couldn't handle learning. It couldn't handle the chaotic, messy environment of the world, which we all interact with all the time very easily. And so artificial intelligence turned out to be not as easy as all that. So we moved on to connectionist systems, which is a lot closer to how the brain actually works. So you have connectionist systems on the left, you have neural models on the right. And this is a lot closer to how the brain actually works. Of course, you have action potentials and neurotransmitters and different weights between the dendrites and axons, but you can abstract out of those computationally to the left to show how these weighted networks that have activation thresholds can process information, and we can code them as well to produce symbolic processing to build common model instantiations that are then handle learning a lot more. They're more flexible. They can handle chaotic environments a little better. We're still learning. We're still building. We haven't figured it all out yet. But
there's a question like Nengo.
Yeah. Yes, like Nengo, exactly, like Spawn, exactly. So you can use code to program these weighted networks, these connectionist systems to actually go about symbolic processing. And it's pretty exciting right now. So in the lab that I work in, the cognitive modeling lab, there is some work in that. And it's messy, but it's a lot of fun. Okay, so actually let's pause there because we get into a different stream. Okay, so connectionist is where we're at right now. Moves up from symbolic processing. And I'm gonna pause to see if there's any questions. But yeah, Spawn is one architecture or one way of programming architectures. And again, why do we want to do all this? We want to have an understanding of how the mind works, all the different functional processes in the mind, because it's been a dark house, as Freud said, for hundreds of thousands of years. Humans have always lived in a dark house. And now we're turning the lights on in that house. And this is one way to do it, to build models, to build architectures, to blueprints that give us insight into what's going on in these different rooms and how they interact. So another benefit of having cognitive architectures that depict different rooms in this house is we could build is when we're building little machines that can help us. This is called machine theory of mind. Not only does it give us an understanding of how the mind works, it can give robots an understanding of how we work. So they usually just take things very literally. They don't understand how humans think. So if you ask a self-driving car, get me to the airport as quickly as possible, you want to hope it doesn't take you literally, because you may not make it there alive or without the law chasing you. It has to understand what you mean. It means not literally get me there as fast as possible. It means as fast as the law allows, as fast as it's safe, is legal, etc. So by creating a theory of mind of machine, putting this cognitive model into a cognitive architecture, into robots, into machine helpers, it can then help robots understand how we think, so it can engage with us more effectively and more empathetically, if I can use that term. So let's pause there. I want to know, are there any useful ways that people can think of that machines that understand how we think a little bit can be useful to us? How could intelligent robots help us? Robots that understand how we think, how could they be helpful to us? Just kind of put it into the chat there. What are useful ways that robots can help us?
Okay, so some of the answers are therapy. A decision-making robot would be great. Everything. I wouldn't mind an intelligent robot that could clean my kitchen for me.
Yeah, right? It'd be great. Make your bed, cook your food,
yeah.
Drive you to work.
Disaster response.
Good, yeah, disaster response. Mm-hmm. Those are all good. Anything else? That's a good start. Mm-hmm. And why for example, I mean, very simply, I mean, you want it, if there's a robot helper, you want to get your order right. You want it to understand what you mean. When you say, flip the eggs, it doesn't mean just keep flipping them forever or keep flipping, it'll ask, it'll interact with you to understand what you mean, not just what you're saying. In medicine, for example, you really, really want a machine to have a working understanding of how humans think, to give patients the kind of care they need when they're in a very vulnerable situation. So
we got a related response in the chat for things to help with everyday tasks so disabled people could be independent.
Yes, exactly. Right. Yeah, good. And you don't want them to be these brusque, unempathetic things that are just these tin cans with no understanding of, otherwise these machines will see humans as an alien, just utterly incomprehensible. So by putting an architecture of how humans think in robots, it can then depict the processes of human cognition and then run simulations to see how it can interact with us to serve our well-being. And by taking care of the disabled or people in medicine, there are already robots being used to help interact with autistic children. It's a way of helping them break out of their worlds and interact with agents. Again, we talked about robots to help maybe with elderly care, with the disabled, and you want them to be nice. You want them to understand the vulnerable position that humans are in, and how to interact with as well. And without an architecture, or without some sort of model of how humans think, it won't be able to interact with us, to our well-being. And if you play video games, you want NPC characters. Here's another one that's I'm a little selfish about myself. You want them to act like people. You don't want them to be these strange robots that just say the same lines over and over. You want them to be convincing versions of humans if you're playing games. And there's actually a lot of work trying to use neural networks to collect information about how humans act, so that these NPC characters in games will interact with us in a way that's convincing, so that they're less blocky, less robotic, and can kind of be flexible. Okay, so those are some ways by which a cognitive architecture put into a robot can help serve human well-being in a better way. So, was there anything else in the chat there before we move on?
One other example or idea was manual labor.
Yeah. I guess, yeah, exactly. You definitely want them to understand what you mean. Okay, so let's see. Maybe this is a good time to go into breakout rooms.
Sure.
Okay, so here's some questions.